Understanding buffers actually is going to help us with our titration calculations. And again, the goal here is just to be able to find the pH at any point in the titration. If you add any amount of acid to any amount of base, I'd like you to be able to figure out the pH. Now, we're going to focus our titration analysis, our acid and base analysis, to 4 possible scenarios. They're called strong acid plus strong base plus strong acid, weak acid plus strong base, and weak base plus strong acid. The nomenclature here is kind of important. The first thing listed is what you start with in the beaker, in the little Erlenmeyer flask. And the other thing, the second thing listed, that's what's in the burette. So in the SA plus SB, strong acid plus strong base, you would have an acid down below and you'd have a base in the burette. So you'd slowly add in the strong base to the strong acid. Now, if you have 2 strong systems coming together, we saw in the last chapter that the pH should be about 7. So the equivalence point should be about 7 for strong acid plus strong base. Now, the second one, we're starting with a strong base in the beaker under the burette, and we're slowly adding in the second part, the strong acid. So the strong acid is being added to the base. So that solution will start basic, because that's what the first part is, and it will get more acidic as you add more strong acid. But strong bases plus strong acids should also have a pH equivalence point of about 7, and that'll be a nice way to see it. Now, we're also going to look at if you start with a weak acid and you slowly add a strong base to it. Now, weak acid plus strong bases, we saw in the last chapter, the equivalence point will actually be slightly basic, greater than 7, because when the moles are equal, all of the weak acid will have turned into a weak base, and bases make the pH get greater than 7. And then finally, we'll look at weak base plus strong acids, where you're starting with a basic solution, and it's getting more acidic as you add strong acids. The equivalence point we saw in the last chapter, a little bit less than 7, because when the moles are equal, the weak base has been turned into its conjugate acid. Acids make pHs a little bit acidic. These titrations, all 4 of these titration types, we're going to separate them into regions, and each region will have its own pH formula, and the pH formulas will repeat. So we're going to see that some of the SA plus SB equations will be used in the SB plus SA region. Buffers do become important when you have weak acids plus strong bases and weak bases plus strong acids. So we will use equations like the Henderson-Hasselbalch when we get to those particular regions. In the lab, there's a titration calculations lab we're going to do, and that's going to give a lot of practice with all 4 of these types of titrations. So I'm hoping that these notes will augment the lab notes and the lab lecture a little bit more. In addition, there is a titration guide on the website that you can use for different regions to see what's happening. So let's talk about these 4 types of titrations. When you're doing these, remember that strong acids and strong bases annihilate their opposites. In a chemical world, which doesn't really use an annihilate, we would say that it makes the K of the reaction very product favored. We're going to assume to use one-sided arrows for those. So strong acids and strong bases don't coexist very well, shall we say, with anything. Weak acids and weak bases, though, do produce their conjugates, and this is what leads us to buffers and some weird pH effects at equilibrium. And those will also be important as we go through all of this. Ka and Kb can be determined through titrations. So there's several different ways to figure out these Kas and Kbs. But in this lab, we're going to look at how people calculate these equilibrium acid and equilibrium base constants. It's a really nice way to do it. If you have discovered a new weak acid or weak base, you can use a titration to actually figure out what the Ka and Kb values will be. Ka times Kb is always equal to Kw, assuming that they're conjugates. That also assumes that you're at room temperature. And again, in this class, we're basically at room temperature. If you do research with acids and bases in medicine, you may need to reconfigure because the body is not at 25 degrees Celsius. pKa and pKb can be helpful. Remember, pKa is minus log of Ka, pKb is minus log of Kb. And pKa plus pKb also equals 14 14 if they're conjugates and you're at 25 degrees Celsius, just like pH plus pOH equals 14. You almost always need to know the initial concentration and volume of the titrant. Sometimes you can calculate it, but almost always you need to figure this out. Sometimes it'll be given to you, and sometimes you need to figure it out. You can also figure out the amount of titrant needed to reach equivalence, and we'll talk about these as we go through this section.